Okay, so we are on the problem three, in which we have different cases, and we are actually talking about the Archimedes principle. Water displaced weighs equal to the weight of the floating object. Always we will see this principle. Water displays the weighs equal to the weight of floating object. The object that will float in the water, then its weight equal to its weight. Water displaces the weight of the floating object. Okay, here we have three cases. First case, you pick up the dumbbell and drop it into the pool. Now you're picking that dumbbell from the boat and dropping it into the pool. What will happen? Second case,
Will it stay the same in all of them?
we will see it. Will it change or not? Second case, you drop the block of wood into the pool.
Oh,
Then
except
what
for
will
the last
happen?
one.
And the last one is that you manage to get out of the boat. Finally, you are actually dropping yourself from the boat into the water. These are three cases. But before these three cases, I want to discuss the density properly. Density is actually the mass per unit volume. We have to check which element is having heavier density and which is having lower density. First of all, let us talk about the dumbbell. Dumbbell is actually having heavy mass as compared to its volume. Low volume, but bigger mass. So its weight will be more, so its density will be more. Low volume, but bigger mass. So mass to volume ratio for the dumbbell will be high. Second case is actually a wooden block. What do you think about the wooden block? Will it sink or float on the water? Absolutely, it will float on the water. Why? Because in case of the wooden block, as compared to the mass, its volume is more. As a result, its density is low. Because of low density, wooden block is floating on the water. Third case, he is talking about himself that he is stepped down in the water, then what will happen? Actually, in the third case, when he will step down from the boat, then he just move in the water. He will not float. His feet touches the ground or the floor of that pool. So here it is not a floating case.
No, I think you're getting out
So
the boat without touching the water. So you will just go out of the pool in the last example.
no. You managed to get out of the boat without touching the water. Without touching the water, the rest is unchanged. Get out of the boat without touching the water. If you will consider that he is just leaving the pool, then that can be another case. We can also discuss if he is leaving the pool and right, like previous two examples, he is moving into the water, then what will happen? We have to discuss.
Mhm.
So, our first case, let's come back towards our first case. But first of all, initially, none of these is moving away from the boat. Boat is actually floating in the water, and it is we're displacing the weight of equal weight of the liquid within the pool. So this boat is actually displacing the equal weight of water in the pool in the first case. Because all these things are within the boat and they are actually performing as a single weight. As a result, boat is displacing more water as a result of their heavier weight.
Sorry.
Okay. Okay. But initially, none of these is actually sinking in the water. All these are floating because of that boat.
Mhm.
But in the first case, we are saying that we need to pick up the dumbbell and drop it into the pool. What will happen? First of all, that thing we have decided that it is actually having heavier density. It will not float, it will sink. If
Mhm.
it is sinking, then the water that will be displaced will be equal to its weight, not equal to its volume. equal to its volume, sorry, not equal to its weight, because weight is actually on the floor of the pool, touching the pool, not suspending in the water. So here, in case of the dumbbell, weight of the water is just displaced according to the volume of the dumbbell. That is actually the low amount as compared to bigger boat.
Mhm.
As a result, a little bit water as compared to the initial case when maximum weight of the boat, when three things were within the boat, maximum volume of the boat weight was displaced by the water weight. Now you need to compare with the initial condition. Now that dumbbell is within the water. If the dumbbell is within the water, then weight of the boat is now reduced. As a result, it is not equally covering displacing the weight of the water according to its initial weight of the boat, because dumbbell is not in it,
Mhm.
and neither it is floating. It is at the beneath on the floor of the boat.
Mhm.
As a result, now the boat a little bit level of the water will come down.
Mhm.
Have you understood?
Yeah, I understood.
Now a little bit water level will come down. So second case is the answer of this option, down.
Mhm.
Water will move down because the weight of the boat is now reduced, and that dumbbell is moved as the downward, and it is not floating in the water. So equal weight of the water is not displaced by the boat. So actual weight displaced by the boat is now reduced. As a result, water level is down.
Mhm.
Okay, fine. Second case, you drop the block of wood into the pool, while the other are unchanged. You drop the block within the pool while the other are unchanged. What does it mean? Still, dumbbell and you are in the boat. You are just moving the wooden block from the boat into the pool. Now, what will happen to the level of the water in the pool? As the block having the weight is not sinking in the water, it is still floating on the water, and its equal weight water is displaced within the pool. So there is no change because it is floating, it is not sinking, it is actually contributing its actual weight that it was contributing into the boat.
Mhm.
So equal amount of the water will be displaced that was in the initial case. So in the second case, it will stay same. The third case, you manage to get off the boat without touching the water. The rest is unchanged. You have get off the boat. Here we can consider the two cases. If he is getting off the boat and getting within the water, then what will happen? Just for example, it will be the case like the first part,
Mhm.
as he is getting off the boat and is moving in the water, and his volume mass to volume ratio is less as compared to the combined mass to volume ratio of the boat and three elements within the boat.
Mhm.
As a result, he will displace the water within the pool, but that water will not be equal to its weight. That water will be actually equal to its just volume of the body.
Mhm.
As a result, a little bit again pool level will come down. As a result, second option is perfect in this case. But on the other hand, if you are thinking he is just going out from the boat, moving out from the boat is actually reducing the weight of the boat. Still, two things are within the boat. Which two things? A dumbbell and a wooden block are still in the boat. Now they have reduced the boat weight. As a result, according to the Archimedes, boat weight will displace the water equal to its own weight. If the weight is reduced,
Mhm.
then its displacement of the water will also absolutely will be reduced. As a result, water level will change again, and in this case water will always again come down,
Mhm.
because now that person is not the part of that boat system.
Mhm.
Is it clear?
Yes, it's
In the
clear.
both cases, if he will remain in the water, if he will get out of the boat and the water, the option will be the two, water
Mhm.
level will come down. Is it
Yeah,
clear?
it's clear.
Okay, okay. Let us move towards the next question. Okay, let us check its statement. A container is filled with the oil and fitted with both ends with the pistons. The area of the left piston is 10 mm square, that of the right piston is 1000 mm square. What force must be exerted on the left piston to keep the 10,000 Newton car on the right at the same height? He's actually talking about the hydraulic brake system or a car wash system. Consider we have two containers. One is having bigger volume while the other is having smaller volume. And both are having actually the piston system. You can consider this smaller one is having the smaller piston and its area is 10 mm square, just that is the piston. And this bigger one is having the bigger piston whose area is 10,000 mm square. So left piston figure is actually a diagram is inverted. Left is right and right is left here.
Mhm.
The area of left piston is 10 mm square, which is right actually right piston here 10 mm square. And that of the piston right, which is here actually left is 10,000 mm square. What force must be exerted? Here you need to apply the force on the left piston, but here in the diagram you can see it is actually a right piston.
Mhm.
To keep the 10,000 Newton car, here is your car. I don't have a good drawing, just you need to understand it is a car, okay? Okay. This is actually the car. Okay, what force is needed to apply on this piston, smaller piston, to hold the car on the bigger piston up when car is having the weight 10,000 Newton. And here the rule which is applied is actually the Pascal rules. According to the Pascal rules, if you have a disturbance created, have a disturbance a little bit in a liquid, for example, in an enclosed incompressible fluid at rest, any pressure applied at one point is transmitted to all the parts of the fluid equally. For example, if you're applying the pressure in the diagram on the smaller piston, then this pressure will be equally distributed throughout. She is very interested in this class.
Yes. I don't know what's wrong with it.
She is actually entertaining to you and want not to be bored in this class. Just
Good.
okay. Here is actually in this whole tube, water is filled. Okay. So according to the Pascal law, mathematically we can write F1 over E1 is equal to F2 over A2. Have we started the recording of this class?
Yes, we have.
Okay, good. So, what we want to understand, we want to understand the force applied on the smaller piston. We need to calculate. So, we can consider the smaller piston is having the area A1 and having the force F1, and bigger piston is having the area A2 having the force F2. You can say here we need to place the car.
Mm-hmm.
So, put the corresponding values. But before that, I need to create some area. Okay. F1 is the force applied on the smaller, that is the value we have to calculate.
Mm-hmm.
While area 1 is 10 mm square for the smaller piston is equal to F2 is the value of the car force, actually the weight of force of the car that is applied on the bigger side of the piston. So that is 10,000 divided by area of this bigger piston, that is also 10,000. So you can cancel this 10,000 by 10,000, then F will be equal to F1 10 Newton. So you need to apply only 10 Newton of force to hold up the car of 10,000 Newton. That is actually the biggest application of this Pascal law. Is it clear?
Yes, it's
So
clear.
first option is correct.
Yes.
Okay. If you want to have a look, please. Okay, yes, here you can see piston A having area 10 mm square, piston B, this bigger piston, 10,000 mm square, and weight of the car 10,000 Newton, and force applied on the left piston to keep the car at the same height we need to calculate. According to the Pascal law, in an enclosed incompressible fluid at rest, any pressure applied at one point is transmitted to all parts of the fluid equally. So mathematically we can write F1 over A1, F2 over A2. F1 is a force on the left, smaller piston. F2 is a force on the right, bigger piston. And putting the values in the above equation, simplifying. So finally we have the relation. Is it clear?
Yes, it's very clear.
Okay. Now let us move towards the question number 5. When a hole is made in the side of container holding the water flow out and flows as a parabolic trajectory. Let us have a container. Suppose we have the container like this, and you need to also consider it is at some height, and in it water is existing. It is very bad container according to the drawing. Okay, now you need to create a hole in it. Suppose this is actually the hole. From this hole, the water will come out in the shape of parabola downward. Okay, fine. That is first part. If the container is dropped in free fall, suppose this container is at height, just we can consider from the 100 of a meter. This container is at the height of 100 of meter. If the container is dropped in a free fall, the water flow, first option, diminishes, stop altogether, and goes out in the straight line curve upward. Which option will be the suitable when the container will move like the free fall? Initially, the water is coming out from the rest state of the container because water is applying pressure on the walls of the container. As a result, that pressure is rho GH. Rho GH, yes, rho GH. Because of this pressure, water is coming out in the parabolic way. And we have considered that our container is 1,000 of meter up, and now we are actually pushing the container down from the 100 meter. So it is coming down and moving in the form of the free fall. What is free fall? Free fall is actually the state when body fall just because of its gravitational pull. None of other forces acting on it, body is falling downward.
Mhm.
Okay, I hope you have studied about the apparent weight and actual weight in the case of, yes, that was actually the lift of a building.
Mhm.
Have you studied some cases in there?
Yeah.
There, in the case of free fall, the equation that was used was F is equal to, or the tension is equal to M into A minus G. In this case, body is falling with its acceleration is not due to external forces. This acceleration is due to gravity. So acceleration is A is equal to G. Then our this force F is equal to 0. As a result, body is falling with the free fall. If the body will fall free fall, in other words, I want to say it is actually an unaccelerated system of the water and container system. There is no acceleration. If there is no acceleration, then water will not move anywhere. It will stay calm within the container as it will fall because of the free fall state, and there will be no acceleration, so there will be no motion of the water from the container, so it will remain same, stop altogether. It will not move. Is it clear?
Yes, it's clear.
Okay. Okay, we have exercise 6. A dam is used to hold back a river. The dam here has height 12 meter and width 10 meter. Determine the net force on the dam. We have to determine the net force on the dam. Okay, dam is actually some type of the big container without roof, and its height is, suppose we are considering our dam is like this, having the bigger height as compared to its width, so I'm making the height bigger, 12 meter, and its width is 10 meter. This is our dam in which water is lying here. What is the question? Determine the net force on the dam. The water is actually applying the force on the dam continuously, and water will never stay calm. It moves because of the airflow. As a result, sometimes its height can be bigger, sometimes its height can be down. So, and one thing more, we also know the density of the water is equal to 1000 kilogram per meter cube, kg per m cube, kg per m cube. So, here, as the total height is h, but because of the just motion, height can move up and down. Okay, yes. Then pressure will also be changed, while the relation for the pressure is equal to P over is equal to F over A. And here someone can say pressure is actually inversely proportional to the area, but pressure is actually the ratio of the focused force on a specific area. If area will increase, then that constant force distribution will increase. As a result, pressure will be reduced. If the area is small, then that constant concentration of the force will be just on that small area. As a result, total magnitude of the force on that small area will be high. As a result, pressure will be high. Such type of question we also will discuss. For example, you are applying a force on a needle just to push it, then you want to pin it, then the force that on the needle or the pressure on that needle is high because that concentrated area is just a little small, and on its magnitude of the force is higher. As a result, pressure in that case is higher. For example, if you have a bigger block of wood and you want to apply the force on that, then that force will be totally distributed on each particle of that block. As a result, in that case, force per unit area or pressure will be low. Is it clear?
Yes, it's clear.
Okay. So pressure is equal to F over A. Then F is equal to P multiplied by A. But here height is not specifically known to us. It is changing because of the water flow up and down. It can be high, it can be low, but the maximum height according to the dam height is h is equal to 12 meters. So maximum it can be 12 meter. So as we don't know, then we will talk about the differential part of the force according to that height is equal to pressure P multiplied by the area. If you want to calculate the area of this dam, you need to multiply height with the width, then area will be calculated. So pressure multiplied by width multiplied by height, because width is not getting changed, it will be the constant, just its height will changed continuously because of the flow will not be calm in the that pool or in the dam. So maximum height, as we know, is h. We need to integrate this equation df 0 to f at each maximum height of the dam. Applied force will be also maximum. So we can write P W multiplied by D H. Initial minimum height of the water in the dam can be 0 when there will be no water in the dam, and maximum height will be H when there will be the total water in the dam. And also we know the value for the pressure P is equal to rho GH. Then we need to replace that value in this equation. Pressure uh, rho G H W D H, from minimum height covered by the water 0 to the maximum height H. So density of the water is constant, gravity is constant, width of that dam is also constant. The only the thing that is getting changed is height. So we will consider height only the variable in this case. You need to move the other things outside. Rho G W sine of integration 0 to h height h dh is equal to force F. So as a result of integration, we will have the relation is equal to rho G W H square by 2 and limit 0 to H is equal to force F. After putting the limit, then our equation will become F is equal to 1 by 2 rho G W H square. Now you have all the values that you need to put in this equation. Then our equation will become 1 by 2 multiplied with the density of the water, that is 1000, multiplied by G, that is 9.8, multiplied by W width, that is 10, multiplied by square of height, that is 12 square. As a result of this, mathematically you have 7 cross 10 raised to power 6 Newton force. That is actually the force in that case applied within the dam of height 12 meter and width 10 meter. Is it clear?
Yes, it's clear.
Okay, you need to have a look here. Height 12 meter, width 10 meter, density 1000. Initially, we are considering average pressure on the dam because of the height to continue change all the time in the flow of water. So average pressure is equal to pressure at the half depth. So, but it will not work. So we have actually changed our mind. So force on the strip, we need to calculate according to the differentiation and integration. So simplifying and putting the value, taking the integration, rho g w h square by 2. Our final formula is h square, and put the corresponding values, and finally you have the results. Is it clear?
Yes, it's clear.
Okay. Okay, we have question number 8. It is
7.
also, yes, 7. You're very attentive, so it is your test. A rock with mass 540 gram. Mass of the rock is 540 gram. In air, this mass is actually in the air. Found to have apparent mass 340 gram when submerged in the water. Its mass on the air was 540 gram. Now it is getting submerged within the water, and its mass is now 2 grams when submerged in the water. What is the volume of the rock that we have to calculate? Okay, its initial mass you are observing within the air is 540 gram, while in the water it is 342 gram. Why is it reduced? Because of that buoyant force that is providing its initial push. Buoyant force actually creates the sense of lightweight within a body. For example, if you ever face a pool swimming scene, then your weight is feel like light, but that is not actual weight. That is actually the apparent weight because of that beyond force that act opposite to the direction of your you can say uh, jump within the water. Is it clear?
Mhm.
Okay. So here I need to write apparent weight. Actual weight is 540 gram is equal to 540 gram, and its apparent weight MA is equal to 342 gram. What we have to calculate? We need to calculate what is the volume of the rock. We need to calculate the volume of the rock while weights are given. When the rock submerged in the water, it experienced an upward buoyant force, as an Archimedes said, buoyant force equal to the weight of the fluid displaced. So, in this case, the weight of the fluid is displaced by the that stone, so it will be equal. Because of this upward force, the scale reads smaller mass in the water than in the air, about which we have already talked. So, in this case, the
Wait, hold on.
buoyant force, yes,
Sorry, my sister's cleaning. I told her to go
it's
away.
okay. It's okay. So already we have worked on the relation like this. In this case, buoyant force is equal to the weight of the stone in the air minus weight of stone in the water, as this buoyant force is causing to be the creation of apparent weight, because actual mass is 540, within the water it is 342. The creation or the reduction of in this mass is seems because of that beyond force that is creating a sense of light weight within the stone. So this actual weight we have to subtract from the weight of the in the air minus weight in the water, then this apparent weight will clear the relation or the value for the beyond force is equal to W air minus W. So you can say it is our equation A, but we are given the mass, we are not given the weight, so we need to subtract the mass. Wm is equal to mass in the air, that was 542,
So you said W?
minus W is for the weight. It is stand for the
Yeah,
weight.
the for where you're. Oh, okay, the change in the weight. Okay, now I understood what you wrote. Okay.
Yes. First of all, we are calculating actually the change in mass.
Hmm.
Then, in this case, we will have the apparent weight, and if for that apparent weight, we will be able to calculate the buoyant force. That is actually the cause of that apparent weight
Yeah, it's
is equal
540
to
minus 342, I think.
192 gram, 198 gram. Change in mass is gram. You need to convert it into the kilogram. Then it will be 0.198 kg, that is actually the apparent mass of that stone. And for the beyond force, you also have the relation, actual relation of Fb is equal to rho in the air, in the water, as we are talking about the water, multiplied by volume of that is covered during or displaced because of that uh, stone. And also here, the beyond force is actually the missing weight or the apparent weight that is found here. So for that case, we need to also write Fb is equal to del mg. Actually, I am writing this equation in the same way is equal to del mg. Del mg is actually representing the missing weight, while the difference of W air minus W water is actually about the missing weight. So Fp is equal to del mg. What you need to do? You need to compare these two equations, both having the left hand side same, so we can compare this equation. Rho W multiplied by volume V multiplied by G. Keep in your mind, we have to calculate the volume of that stone. Del M multiplied by G. Here you cancel the G by the G and isolate the value of the volume. Then our equation will become V is equal to del M divided by rho water, density of the water. And we know the missing mass or the apparent mass is 0.198. So we need to put that here 0.198 divided by density of the water, that is actually the 1000 kilogram per meter cube. 1000 kilogram per meter cube. Then results will be 1.98 multiplied by 10 raised to power minus 4 meter cube, because we are talking about the volume. But you can convert it into some smaller unit, as we can say 1 meter cube is equal to 10 to the power 6 cm cube. So here you can write 1.98 multiplied by 10 raised power minus 4 multiplied by 10 raised power 6, and it will give you the results 1.98 cross 10 raised to power 2. In other words, you can write 198 cm cube. So the volume of stone within the water is that we have calculated is 198 cm cube. Is it clear?
Yes, it's clear.
Okay, you need to have a look here. Mass in the air 540 gram, mass in the water 342 gram. And keep in your mind, this reduction is mass just because of that buoyant force that is providing the thrust to feel the sensation of the light mass within the water. So when the rock submerged in the water, it experiences the upward buoyant force, as Archimedes said, buoyant force equal to the weight of the fluid displaced in this case. Because of this upward force, the scale reads smaller mass in water than in the air. So, buoyant force is equal to the loss of weight. So, Fp is equal to this, calculating difference of mass, that is here. But also we know the relation for the buoyant force is equal to rho Vg, and we can also write this equation like this is equal to Fp is equal to W del mg. Compare both these equations, cancel the g, and separate the value of the v, because that we have to calculate is equal to del m over water density. Simplifying. So finally you have the density of the stone within the water 198 cm cube. Is it clear?
Yes, it's clear.
Okay.